All right, so last time we introduced a bunch of new reactions that fall under this category of electrophilic aromatic substitution, EAS reactions. And so for each one of these reactions, we take a benzene ring and we're going to substitute the hydrogen on that ring for one of these 6 new functional groups here. Okay, we introduced each of these 6 reactions separately, and then we created this handy-dandy little wheel to help summarize all of those reactions. Okay, we're going to continue to just look at these 6 reactions here over and over and over again today, but we sort of introduced this problem of, okay, if we just do one of them, that's easy enough to predict our products. We're just going to swap out our hydrogen for one of those new functional groups. And if we start out with a blank benzene ring, it doesn't matter which one of those carbons we pick. We're always going to get that same product. But if we try to do 2 of them in a row, so we first do that nitration reaction where we put a nitro group on there. And then we do a second reaction, a bromination reaction. Well, now we have 3 possible products depending on the orientation of those 2 functional groups about that ring. Again, we're just going to put a nitro group and a bromo group on there, but the question is, where are they relative to one another on our ring? Are they right next to one another? Are they 2 removed? Or are they on opposite sides? All right, so this is kind of what we started discussing towards the end of last class. And remember, we talked about how some of these groups are going to be considered electron donating groups. All right, we can spy an electron donating group because it has this pair of electrons directly next to that benzene ring. And these groups can donate that pair of electrons to that ring. Okay, hence the name, electron donating group. So in this one semester, if we were in the 2-semester course, we would spy patterns that we know would lead to resonance structures, and you could draw these structures yourself. We're on a little bit more of an accelerated timeline in this course. So you're just going to trust me that when that pair of electron gets donated to the ring, we can draw these 3 resonance structures here that show that electron being donated, right? So here's my pair of electrons in my original molecule, my phenol. That's now going to be donated to the ring. So now it's going to donate that pair of electrons to that benzene ring. And we can see that pair of electrons shows up around that ring, okay, as it's being passed around that ring, as it's being donated to that ring, but it doesn't show up on every single one of these carbons. It's really only every other carbon that gets hit with that pair of electrons. It's the next door neighbors, these ortho positions, and the para position on the opposite side of the ring. You can see that those meta positions get skipped. Okay, cool. So we have this electron donating group. It donates pairs of electrons specifically to the ortho para position. All right, and remember, in these reactions, benzene is our nucleophile. Which means it's the electron-rich species in this reaction. So if I stick an electron donating group on there, I am making these positions even more electron-rich. They're even better at being nucleophiles because they have that pair of electrons donated to them. All right? So all of that to say is that we use this to illustrate that electron donating groups they make the ortho and para positions better nucleophiles. So what does that mean? So that means that if we have one of these electron donating groups on our ring, and we do one of those electrophilic aromatic substitution reactions, it's going to direct any incoming substituent specifically to those locations there. All right, so our electron donating groups, we call these ortho para directors. All right, they are going to direct any incoming substituent to an ortho or para position. Okay. All right, so what does that mean? Let's just do an example here. Okay, so first of all, let's remind ourselves, if I take this benzene ring and I do this reaction here, everybody take a second and give me my product of this reaction. All right, this is how we substitute a hydrogen for a bromine. And now I'm going to do the exact same reaction, but instead of starting out with just a regular old benzene ring, I'm going to start out with a benzene ring with that electron donating group. And remember, we called these electron donating groups ortho para directors because they're going to direct any incoming substituents specifically to these ortho and para positions. So I'm not going to get a mixture of all three possible products. I'm only going to have two. One where the bromine is in that ortho position, and one where the bromine is in that para position. Okay, what we're going to have, since we have an ortho para director on that ring, is a mixture of the ortho and the para products. Okay, cool. So if we have an electron donating group on this ring, we don't get all three of our possible products. We get only the ortho and the para product. All right, so we talked about electron donating groups. We can also have what are called electron withdrawing groups. All right, and as the name implies, these are going to remove electron density from that benzene ring. Okay, so I'm going to give you an example here. I'll tell you how to spy these electron donating and electron withdrawing groups here in a second. For right now, you're just going to trust me that this is an electron withdrawing group. Okay. And so if we show it doing these electron withdrawings with our resonance structures, okay, again, you're just going to kind of trust me that these are these structures that we get. What happens is this pair of electrons that's in this ring is going to jump out of that ring. It's going to get pulled away from that ring. Got pulled up onto that oxygen, all right? But that leaves this carbon right here with a positive charge. Okay, but just like before, that positive charge is kind of stabilized by being bounced around to various positions on that ring. So these are all of these resonance structures. We'll move one more. Oops. Okay, so these arrows are a little bit advanced for this course. They show the movement of electrons. You can kind of imagine that I'm grabbing a pair of electrons and dragging it over to this new atom. We don't learn how to draw them in this course. Again, you're just going to trust me that these are these resonance structures that these electron withdrawing groups have. All right, and again, what we want to notice is the charge that we have being passed around this ring here. Again, we are hitting specifically which positions with that positive charge. So here's ortho, here's para, here's my other ortho position. Okay, so again, just like before, we've got this charge being passed around this ring here. It's only hitting specific carbons. But unlike my electron donating group, which is donating a pair of electrons, so now it's a negative charge, this is an electron withdrawing group, so it's stealing electrons away from that ring, right? So now every other carbon has that positive charge. All right, and we want to remind ourselves that in these reactions, benzene is that nucleophile, the electron-rich species. If I have an electron withdrawing group on that ring, something that's pulling electron density away, is benzene going to be a better nucleophile or a worse nucleophile? It's going to be worse. It's got less electron density in that ring. All right? And in particular, we can note that our electron withdrawing groups just like before, that effect is not created equally. It's making specifically the ortho and para positions worse at being nucleophiles. So if we have one of these electron withdrawing groups on there, it's not going to direct incoming substituents to the ortho-para positions. Now those positions suck at being nucleophiles, right? So instead, anything incoming is going to be directed to the meta position. So we call these electron withdrawing groups meta directors. Okay? Cool. So let's just take a step back here. We introduced these electrophilic aromatic substitution reactions. If we take a benzene ring, we can do any one of these reactions and it sticks something new on the ring. All right? Cool. Straightforward. And then we introduced this new problem, which is what if we do 2 in a row here? Which one of these 3 possible products do we get here? And what we just did is we said that we're going to break this world into electron donating groups. Electron donating groups are going to prefer the ortho and the para products, or it's an electron withdrawing group which is going to favor the meta product. All right, so how do we spy, or rather, if we're going to sound more fancy about it, how do we classify our electron donating and electron withdrawing groups? So what we're going to do in a second is we're going to go and we're going to look at that wheel and we're going to classify everything as being either electron donating or electron withdrawing. But we need to be able to spy what's what here. All right? So the easier of the two is going to be our electron donating groups. All right, and that's because we already talked about this structural feature that they have. We demonstrated that with phenol here, and that is the fact that there's this lone pair of electrons that's directly next to the ring. It's right next door and can be lent to that ring. All right, so our electron donating groups, they have lone pairs directly next to that ring. Okay, so let's look at our 6 electrophilic aromatic substitution reactions. There are 2 that we can spy as being electron donating groups. Everybody take a second and see which 2 we can spy as being electron donating groups. And I'm going to be good and I'll draw out the full Lewis structure of that nitro and sulfonic acid group just so we can make sure. All right, we got 2 electron donating groups. Which ones are they? Yeah, the 2 halogens, right? So this is an electron donating group. I'm just going to label these ED, or electron donating. All right, well, what about this nitro group right here? It's got a lone pair here and here. It's not directly next to the ring. Okay? In fact, what's directly next to the ring is a positively charged nitrogen. So this thing isn't going to donate electrons. It's actually going to withdraw electrons, but we'll get to that in a second. All right? Based on that first rule, we can classify these 2 as being our electron donating groups. Okay? There's one more group on here that doesn't fit that same pattern, so we're just going to make a note. Electron donating groups have lone pairs directly next to the ring, or they're alkyl groups, which remember means all carbons and hydrogens with single bonds. Okay, so going back here, there's going to be one more. Which one can we do? Our alkyl group is going to be these R groups here. Remember, we use that as our variable for any number of carbons and hydrogens. So these Friedel-Crafts alkylation reactions will also create electron donating groups on that ring. So then what about our electron withdrawing groups? All right, these are simply just going to be everything else, right? Everything that doesn't follow one of those two patterns as being an electron donating group is considered an electron withdrawing group. So our electron withdrawing group is simply everything else. Okay? So then if we go back here, let's just finish labeling our wheel here. We got our 3 electron donating groups. That means that everything else, also our sulfonic acid group is electron withdrawing. Our nitro group is electron withdrawing. And that acyl group is electron withdrawing. Okay? And remember, what's the real consequence of being an electron donating group is that you are what we call ortho-para directing. So everything that we just labeled as being electron donating, these are ortho-para directors. And what about our electron withdrawing groups? Meta directors. All right, so we talked about how we can have, here's our little ring now, summarized all of our 6 reactions that we talked about, plus whether these groups are ortho-para or meta-directing. And that's what we're going to have to consider when we start doing these reactions one by one, right? When we start pairing them up. Okay, cool. So let's do 2 examples that we're going to stack directly on top of one another so we can make sure to see. What we're going to do is we're going to take the same 2 reactions, but we're going to switch the order here. So the first thing I'm going to do is that fuming H2SO4, and then second I'm going to do that Friedel-Crafts alkylation reaction. And then in my next example, I'm going to take these same 2 reactions and I'm just going to flip the order here. So now the first thing I'll do is that alkylation reaction, and the second thing I'll do is that sulfonation reaction. All right, and everybody just take a second and give me the products of these 2 multi-step reactions here.
You want us to draw the formula structure for the H2SO4?
No, you don't have to draw. No, you can just leave it. Importantly, on your homework doesn't accept an abbreviated structure, so you'll have to draw it. So that's why we have it in our notes. On pencil and paper, you could SO3H is perfectly fine. All right, if we look at this first one first, let's sort of break it up into these two steps. Oops. All right, so after step one, my sulfonation reaction, I'll have put that SO3H group on the ring. All right. And my next reaction here is going to stick that methyl group, that CH3, on the ring. But again, I got these different positions. My ortho, my meta, and my pair position. And I got to determine which one it's going to go to. Okay? Now, importantly, the methyl group, the thing that I'm adding, that doesn't get to decide where it goes, right? It's not like the incoming group is going to choose one position or the other. It's what's already on the ring, that sulfonic acid group, that is changing the character of that ring, which is what's leading to that specific product. So importantly, I'm not going to look here. I'm going to look at what's already on the ring, all right? And I got to ask myself, is this thing ortho-para or meta-directing? What did we say for these SO3Hs, our sulfonic acid groups? These are meta-directing groups. So in terms of my possible positions for my incoming substituent, it's going to be that meta position, right? So after I do that second reaction, I'm going to get my product with that methyl group in the meta position. There's only one meta position. If regardless of which one I chose, I'd get this same product, so I can just pick one. Cool? All right, so again, important to remember, the incoming substituent doesn't get to decide. It's what's already on the ring that is going to direct the incoming substituent to one of those particular carbons. So now if we do these same two reactions, but we do them in a different order, now my first reaction is going to be that alkylation reaction. So now the first thing I put on that ring is going to be that methyl group. And when I do my second reaction, I'll put on that SO3H, but again, I got to figure out where to put it. So I'm going to look at these alkyl groups here, and we call these alkyl groups what? Orthopara or metadirectors?
Orthopara.
These ones are orthopara-directors. So it's going to specifically direct to those ortho and para positions. So after my second reaction here, I'm going to get a mixture of these two products. All right, I'll get a mixture of the ortho product and the para product. All right, so same two reactions that we did. Let me kind of clean this up. Kind of just have these stacked on top of each other so you can see more clearly. Okay, I did the same two reactions, I just changed my order. In the first example, I did my meta-directing reaction first, or rather I put on a meta-director first. So that's why we get our meta product as our final product. Whereas in my second reaction here, the first step was to add an ortho-para-director, which is why I get a mixture of these ortho-para products. Okay, so again, same two reactions, but we could see how the order in which we perform them is going to dictate what product we get. Cool. All right. So now we got two more reactions that we're going to introduce. They're sort of closely related to these electrophilic aromatic substitution reactions, but not quite. We're going to learn how to take these groups and turn them into something else. So let me just show you what I mean. Let me get my good benzene ring. So if we take, for example, that nitro group, all right, we can take nitrobenzene and we can reduce it to aniline and H2. All right, so notice in this reaction, I've swapped out those two oxygens on that nitrogen for just two hydrogens instead. All right, let's actually do our full Lewis structure here just to be good. Okay, if we do this one here. On my product side, my nitrogen has 3 bonds, so what is it missing here? Lone pair. All right, and we do this with a set of reagents that you're just going to have to sight memorize. It really doesn't sort of make any sense. We're going to use zinc and HCl, followed by sodium hydroxide. Zinc is a metal that is particularly good at donating electrons, and that is what's happening in this reaction here, but that's about the extent of what we're going to say about it. Magic, all right? Well, how does zinc and HCl do it? Again, magic, okay? Trial and error, that's how they know. Yeah, zinc you do see kind of a lot in organic chemistry specifically because, again, as a metal, it doesn't hold on to its electrons very tightly, and that's kind of key here. But for right now, you're just going to trust me. Zinc HCl and NaOH will convert that nitro group into aniline, right? This one right here, just to be clear, we had a special name for this benzene derivative, aniline. That's why I keep calling it that. Yeah. But key to what we sort of just discussed here, when I look at that nitro group, I classified that as what? Orthopara or meta-directing? This was a meta-director, right? There's no lone pair directly next to that ring. So this one was a meta-director. All right, and then let's remind ourselves, our electron donating groups, we said we can spy them because they have lone pairs directly next to the ring. So when I look at my product here, what would I say about that nitrogen? Is it orthopara or meta-directing? Orthopara. Now it's an electron donating group, which makes it orthopara directing. All right, so the key here for our reaction is we're not adding anything new to our ring, but this is a reaction that converts our meta-director into an orthopara director. Okay. One more reaction that we can throw into this same category here starts with not nitrobenzene, but one of those Friedel-Crafts acylation products where we have that carbonyl carbon next to the ring. Right? And this reaction is going to just chop off that carbonyl oxygen. All right, this has an obnoxiously similar set of reagents where we see zinc and HCl again, but you don't have to do a second step with sodium hydroxide, you just heat it up. Again, we're just going to trust the organic chemistry gods on this one. Yeah, zinc is doing something similar. It's again donating electrons, but beyond that, we're not going to say much about it. All right. But importantly, again, if we go through and we classify here, this group, our acyl group, we classified as what? Orthopara or meta-directing? Meta. And what about these alkyl groups over here? Orthopara. That was our second category of orthopara directors, was those alkyl groups. So again, I've converted my meta-director into this orthopara director. Cool. All right, so let's just do a few examples, again, kind of stacked on top of each other. All right, I want you to do first a nitration reaction, and then follow that up with a bromination reaction. All right, so that first step sticks that nitro group on that ring. And then the second step is going to stick a bromine on that ring, but specifically in what position? If I look, my nitro group is a meta-director, so that will direct that incoming bromine to the meta position. Remember, the bromine doesn't get to pick, right? It's the thing that's already on the ring, the nitro group, that is going to direct it to a specific location. Cool. So now we're going to take this same set of reactions here. And I'm going to add this last step at the end, last two steps of doing that zinc, HCl, and then NaOH. So if we look up here, I'm going to break this up into each individual step here. The first step adds a nitro group. Now I'm going to do my second step where I'm going to add a bromine. But since this nitro group is a meta-director, I'm specifically going to put that bromine on that meta position. All right, and now the next steps, we got to do 3 and 4 together. As we discussed, this zinc HCl and NaOH combo will convert our NO2 group into an NH2 group. All right, so my final product here will be NH2 instead of NO2 and our bromine. If I'm going to be good, I'm going to put in my lone pairs here. Cool. Okay. Now, notice how we talked about how this thing was an orthopara-director. My bromine is here. Well, that's because when I put the bromine on the ring, what was on the ring? A meta-director. Right? When I change that NO2 to an NH2, it's not going to pick up the bromine and move it. The bromine's already on the ring. All right? The difference here would be now let's do these same 4 reactions. But now I'm going to change up the order here. I'm going to do the bromination step at the very end, and I'm going to move that zinc HCl NaOH to the middle. All right?
Can you go back real quick?
Yeah. All right, so I do that first step, it's the exact same. I put a nitro group on that ring. But now when I do steps 2 and 3, that nitro group is going to be transformed into an NH2. All right, and even though my nitro group is a meta-director, when I do steps 2 and 3, I'm going to transform it into an ortho-para-director. So that when I do that final step, my bromination reaction, my bromine's going to be directed to the ortho and para positions. Okay, so I'm going to get a mixture of my two products. I'm going to get a mixture of my ortho bromoaniline and my para bromoaniline. Okay, so again, same set of reactions, but the order in which we perform these reactions is really important in determining our products. Let me just kind of move these next to one another. Oops. Okay. At the end of the day, we still get bromoaniline in both of these pathways, but the difference is the orientation of those two groups around our ring. If I save that zinc HCl NaOH step for the end, I will get my meta product. But if I do it right after putting the nitro group on there, now that's my director, and I'll get the ortho and the para product. All right, so we need to be able to follow these electrophilic aromatic substitution reactions, meaning that if I give you benzene and a list of reactions, follow them to give me my correct product, right? Again, attaching your thing to the ring and then asking yourself, is this an ortho-para director when you move on to the next step? All right. What's a little bit more challenging and what we're going to work on now is you figuring out your own synthetic pathway here. All right, synthesis strategies. Meaning I'm going to give you a benzene ring. And I'm going to give you a target product. And you need to tell me how to get from A to B here. All right, your goal is to fill in this reaction arrow here with any missing reactions that we need in order to create this final product. All right, so importantly, when we look at our product here, we need to be able to say, all right, I know how to put this thing on, and I know how to put this thing on, okay? You don't have to have your reagents memorized, okay? You will have those given to you on your exam, but importantly, you need to spy what does what, all right? Now, we obviously have this master cheat sheet reaction wheel that we built, but if you're doing this with your homework, I mean, that's not a bad place to start, but it's kind of a little bit too much information, right? You won't have this on an exam to reference. So what I would do if I was trying to study is instead of using my cheat sheet to do my homework or at least to practice for the exam, I wouldn't use that full cheat sheet. I would create some sort of a reagent bank here where I sort of list, okay, I know that I have bromine and aluminum bromide, that's one. Chlorine and aluminum chloride. HNO3, sulfuric acid. Our fuming. H2SO4, etc., etc. And I would use my reagent bank to try to do those problems, right? If I can do my homework problems with just the reagent bank, not having to use that full cheat sheet, that means I'm good to go for the exam. That means that I can spy what each one of these are supposed to do without having to cheat, okay? So, well, you can create, the rest of your reagent bank using those other reactions from our wheel. Let's stick with these four right now and see if we can't match with our problem. Okay, I'll just drag that up there actually. All right, so given my reagent bank here, how do I put a nitro group on the ring? That would be this set of reagents right here. And how do I put that sulfonic acid group on the ring? That's my fuming H2SO4, right? So I need to spy which reaction is going to do which one of these things. And now the hard part here is the order in which I do those two reactions, right? I got my two reactions that I need. What order do I do them in to get my desired product? All right? So the other thing that I'm going to do is I'm going to look at these reactions and I'm going to say, all right, what are each of these groups? That nitro group is what? An orthopara or a meta-director? Meta. And what about that sulfonic acid group? That one's also a meta-director. And if I looked at my product here, what is my orientation? Are these two groups ortho, para, or meta to one another? Meta, okay. So for this particular example, it doesn't matter my order. I got my two reactions, but since either one are ortho, para directors, I would have two correct answers here. First, doing my nitration reaction, and then using fuming H2SO4, or I could do it the other way. And both of these would be full credit answers. Okay, either one of these would give us our desired product, where a nitro group and a sulfonic acid group are what meta to one another. All right, so let's do a slightly harder one then. Again, we're going to start out with our naked benzene ring, and we're going to put a bunch of functional groups on it. All right, here's our little reagent bank here. All right, see if you can't tell me what reactions and in what order we would need to create this particular product. All right, let's label these reagents, A, B, C, and D. Which one am I going to need to put on that nitro group? C. And which one am I going to need to put on that chloro group? B. Cool, so we have our reactions, and now we got to think about the order in which we're going to do these two reactions, all right? So I'm going to look at my nitro group, and I'm going to say, all right, is that an orthopara or a meta-director? Meta. Whoop, not me. Meta. And if I do my chloro group, is that an orthopara or a meta-director? That one's orthopara. And in my product here, where do those two functional groups sit relative to one another? Ortho, meta, or para? So this is my para product, which means that the first reaction I'm going to have to do is one that will direct the next thing to that para position, right? So first, I'm going to do that chlorine and aluminum chloride, and then after that, I can do my nitration reaction. Okay, now, You might say, well, won't I get a mixture of both the ortho and the para product? Yes, absolutely. But importantly, you have to do them in this order if you want any para product at all. If you reverse these two, you would not get that desired product. So yes, if you were in the lab, you would do this and you would have a mixture, and you would use one of the million techniques that we have in organic chemistry called chromatography to separate out these two components from the mixture, right? So I'm not saying that this is the only product, but importantly, that is how you would get that particular product. You would first have to put on that chloro group because it's an ortho-para director, and then the nitro group would be directed to the correct position, okay? So again, all of this goes to say we're going to use those same reactions over and over and over again, but the order in which we do them is going to be really important. All right? I guess let's just kind of take this last few minutes here to complete this reagent bank just so we can be clear. All right, I was trying to go a little quick so we could squeeze in some examples. We have two more electrophilic aromatic substitution reactions that we learned, which both had those fancy scientists' names, the Friedel-Crafts reactions. All right, we had our Friedel-Crafts alkylation reactions and our Friedel-Crafts acylation reactions. So these are our 6 reactions that will put something new on the ring. And then we learned 2 more today which convert one thing to another. And they both had that zinc HCl. But one of them was a 2-step, zinc HCl and NaOH. And the other one was zinc HCl and heat. Okay, so these are these 6 reactions that we need to be able to kind of mix and match from this particular section, right? And we need to be able to do 2 things. If I give you a list of these reactions, 3 of them performed in a row, what product would you get? As well as being able to do the synthesis yourself, sort of designing a pathway of how to get from reactant to product using some combination of these reactions here, okay? And again, like before, I'm not expecting you to have these reagents memorized, but you do need to be able to sight recognize them, know what they do, all right? And in particular, there's 2 that are going to be really challenging to tell apart because they both have zinc HCl in them, right? So you want to make a little note in your mind that distinguishes these 2 here. Cool? All right, that's all I got for y'all.